Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question. And today's question is perfect ranges. In this question, we're given a pair of arrays A and B, both of length n, and they're called perfect if we are able to form an array C that satisfies these two conditions, which are every element C of I is either equal to A of I or equal to B of I for all the n elements, and the array C of I is strictly increasing array, right? So for example, let's say this is our array A, this is our array B. Now to check if it is a valid perfect array or not, what we'll do is we'll try to create an array C. So first of all, we'll take the min of these two. So we'll have two. The next element has to be bigger than two. So the only possible value which we can have is four. The next element could be either of 5 and 7, so let's take 5. The next element would be either of these two, so let's take 8. And the last element could be anything, so let's take a 10. And we were able to form a possible array C, which is strictly increasing. So this is a perfect array, right? This is a perfect possible array. Now in the question, what we are given is, we are given two arrays A and B of length n, and it is guaranteed that each element is in between 1 and 2n, which does not really matter, but yeah. And we need to find how many pairs L comma R exist such that these L and R are in between 1 and n, and the arrays L comma R and B of L comma R are perfect arrays. So we just need to find the number of possible ranges of L and R which are perfect. So let's say we consider this range, which is 2 comma 4, right? Is this a perfect range? Yes. Why? Because we can form an array C which consists of this 1, then this 5, and then this 6. Right? Or it could also be like 1, 7, and 8. But yeah, this will be counted as 1 only because it is a valid possible range. So yeah, that is it for the question. Now let's see the constraints once. So we have the number of test cases in between 1 and 10 is to the power 4, and in between 2 and 2 into 10 is to the power 5. And we are given that the sum of n would not exceed 2 into 10 is to the power 5. So seeing the constraints, we can say that our expected time complexity would be of order, let's say something like big O of n or big O of maybe n log n or something like this, right? Now let's see the sample input ones. So in the first input, we have 2, 3, 6, 1, 4, 5. So the possible ranges would be like the first range would be 1 comma 1 because obviously this is a valid range, right? We can just put 2 and it is a valid range. We can take just this element that is the range 2 comma 2 and this is also a valid range. We can also take just 3 comma 3 and that is also a valid range, right? Next, we can also take these two elements, that is 1 comma 2, and we can take this 3 and then this 6, so it is also a valid range. And we can also take this as a valid range because we can take 1 and 4. The second input, all of the possible subarrays or all the possible ranges are valid. So this, and this. All these six ranges are valid. In the third, we can easily see that the only valid ranges are 1, 1, 2, 2, and 3, 3. So I hope the problem statement is like pretty clear so far. So now let's move to the solution. So we'll begin by how to check if an array is perfect or not, right? So let's figure out a greedy approach for this, right? So initially, it is always best to take the minimum of these two as our C of 1. Why? Because this will give us more chances for the further elements. So if I take a 3 and over here there are like these are just okay, let's say over here it was 4, and if I take 4, and over here let's say there were just 3, both of them were 3. I could not take any of them, right? So it is obviously better to take the min of them. Now, if the next element is bigger, if both of the next elements are bigger than our current element, this element, then we could then it's best to take the min of these two, right? So that we can have more possibilities in the future. Again, both our elements are bigger, so we'll take 6. Now, the only element which you can take is 7. Over here, the only element which you can take is 8. We can take either of them, so it's better to take 11. And again, we can take either of them, so it's better to take 12. Now, notice here that, like, if I'm trying to know that what element should I put between A of I and B of I, the only information I need is what my previous element was. And the previous element would either be A of I or B of I. I mean, A of I minus 1 or B of I minus 1, right? This is the only info I need to know what my current C of I will be, right? So in general, in general, the only values for which index I matters are A of I minus 1 and B of I minus 1, right? So if we know that what my previous element was, I can calculate my current element using this greedy approach. Now we need to count the number of possible ranges, right? So usually like counting problem involves TP, right? And over here we also kind of know the states, right? Because we can easily like put the states as n into 2, where this 2 would represent like if it is 0, that means my previous was A of I minus 1. And if it is 1, that means my previous element was B of I minus 1, right? Makes sense, right? So, and in DP, what do we need to store? We'll be storing that how many ranges and at a particular index, right? This is what we would try to solve, and we'll try to see if we can come up with some transitions or not, right? So obviously, what will our DP store? It will store that starting from anything. I don't know what we're starting from, but how many perfect ranges and that index I, right? So how many ranges L comma I can I get such that my previous element was A of I minus 1 for DP of I 0. Now what will my DP of I 1 store? It will store that how many ranges L comma I we can get, that is like starting from some index L and ending at I, how many such ranges we can get such that our last element was B of I minus 1. Right. And one thing which we really need to make sure is that we are not recounting the ranges. So if we have, let's say, already considered some range L comma I in this 0, 3, right? We're not recounting it inside this because we do not want the total number of counts we can have, total number of RACs we can have. We only want the count of how many ranges we can have, right? So now one thing which we'll do to make our problem slightly easier is we'll assume that A of I is less than or equal to B of I. And if it is not the case, we can easily swap A of I comma B of I. And why can we swap? Like it's very easy to prove. Like the it does not really matter if I have A of I or B of I because we can take either of the element, right? So I hope that just makes sense. Now let's discuss the transition using this example. So what would our dp of 1 be, first of all? What would our dp of 1, 0 and dp of 1, 1 be? Think about it for a second. So inside our dp of 1, 1, we want how many ranges I can get ending at position 1, right? So this will obviously be equal to 1, right? Because there can be just one element which can start at index 1 and end at index 1, right? So like this is the only possible range which I can give, right? Now what would our dp of 1, 1 be? It is like your first thought would probably be like 1 because we can start at 1 and end at 1, right? We can just take this 5. But no, here it would be 0 because we want the count of the ranges, not the possible RACs, right? So we've already considered this range 1, comma 1, and we do not want to recount it, reconsider. So we'll be keeping it as 0, right? Now let's consider the different cases. So let's say we have calculated something up till this index and my dp of this value stores this x and dp of this stores y, right? So dp of I minus 1, 0 stores x and our dp of I minus 1, 1 stores y, right? And now we're trying to calculate the answer for our ith position, right? Now if our a of I is bigger than both of these elements, that basically just means it is bigger than this element because we're assuming that all a of I are less than or equal to b of I. So if our a of I is greater than this element, that means like we knew that there are like x ranges of the form L comma I minus 1 and y ranges of the form some L comma, or I'll just call it L2 probably so that it's not confusing. So there are y ranges of the form L2 comma I minus 1, which are such that like the previous element for this was like this something from this array, and the previous element for this was some element from this B, right? Now I can extend all of those ranges with this I as well, right? Like we know that those elements were ending at 8, right? These elements, all of these x's are ending at 8. So I can extend all of them and put an 11 in the end, right? And similarly for all of those ranges which are ending at this 9, I can extend all of them and put an 11 in the end, right? So what would my this state would be, right? This dp of I 0 be, it would be dp of I minus 1 0 plus dp of I minus 1 plus 1. Why are we adding this one? Because we also need to consider the range that starts from here and ends over here, right? So that is what we put over here. And what would this dp of I1 would be? We have already considered all the possible ranges we could get, right? We have considered all the x ranges we could get, all the y ranges we could get. So it's pretty much useless to put 13 in it, right? Because it's not going to give me any new range. And we've also considered this range, right? So this is just going to give us literally no more info. So this dp of I1 will be 0. That's it, right? Now let's consider the next case. So what if a of I is not greater than b of I? So it could be possible that this a of I is less than this b of I minus 1, but it is bigger than this, right? So now our x is this and our y is this. So if this is the case, then I can extend all of these x's with this 12, right? But I cannot extend these y's with this 12, right? Let's assume it to be 12.5 so that they are not same, but yeah, okay, just leave that. Leave this. So yeah, I can extend all of these x's, all those ranges which are ending at this index, and put a 12 in the end of them, right? So what I can put is dp of I minus 1, 0, and I'll be adding a 1 because I can obviously start a range from this place itself. Now, what about this index? So for this, if this element is bigger than the previous element, right? If this element is bigger than our b of I minus 1, then we can add dp of I minus 1, 1. Otherwise, we cannot. Otherwise, it would just be 0 because we cannot extend any range. So if we can extend any of these ranges from this y, we'll be adding this. Now, why are we not considering x? Because we've already considered those x's in this dp of I0. So we'll not be reconsidering all those ranges. Now, similarly, the last possible case, again, over here, we did not add plus 1y because we have already considered this range, right? So now let's consider the last possible case, that is if our a of I is less than a of I minus 1. So let's say this is our x. One second. Okay, this is our x and this is our y. Let's say this, or probably let's say this is our x and this is our y. So now this a of I is less than both of them, right? So obviously I cannot extend any of my previous ranges, but what I can do is we can start a range from here and end the range over here itself. So what we'll do is we'll keep dp of I0 as 1. That is, we started some range and we ended the range at the same place. Now what our dp of I1 would be? If our b of I, this element, is bigger than the previous element, then I can add all of these x's, right? So if this is true, I can add all of my dp of I minus 1 zeros, right? Why am I able to add zeros this time? Because I have not considered these x's already, right? So these have some ranges L comma this index I minus 1, and I can extend all of them with this 13, right? Now, if this is also like this b of I is also greater than b of I minus 1, I can extend these dp of I minus 1 ones as well, right? And why again we are not adding a 1 over here? Because we have already considered this over here, right? Now, what would be the time complexity of it? It would be simply big of 2 times n, which is nothing but big of n only, right? So yeah, this is pretty much the whole solution. Now let's discuss the codes. So yeah, now let's see the solution in C++ first. So we'll begin by taking the input of n. We'll take in the input of the array A and B. And yeah, for convenience, as we discussed, if A of I is greater than B of I, we'll just swap them so that all the elements are like for all i's, A of I is less than or equal to B of I. Now we'll define our base case, that is dp of 1, 0 is 1 and dp of 1, 1 is 0. Now here are all the three possible cases. So if our A of I is greater than B of I minus 1, so we'll just simply take dp of I minus 1, 0 plus dp of I minus 1 plus 1 as we discussed in the solution, and dp of I1 would be 0. Now if this is not true, that means A of I, and if A of I is greater than A of I minus 1, so we can obviously extend all of these A of I minus 1s with A of I, right? All of those ranges. So our dp of I0 would be dp of I minus 1, 0 plus 1. Now, if our b of I is greater than b of I minus 1, we could extend the b of I minus 1 ranges as well, right? With this b of I. So we'll have this dp of I1 is dp of I minus 1 plus dp of I minus 1, 1. And otherwise, we'll just define dp of I0 as 1 because we can start at I and end at I itself. And otherwise, if our p of I is greater than a of I minus 1, then we can add all of those a of I minus 1 ranges. So we'll add them. And if this p of I is greater than p of I minus 1, then we can add all of these ranges of p of minus I minus 1 as well, right? And our final answer would be nothing but the summation of dp of I0 and dp of I1 for all of the i's. And we'll just simply print that. So this was the whole solution in C++. Now let's see the solution in Python. So we'll start by taking in the input of n. We'll take in the input of the arrays a and b. Now for convenience, if our a of I is greater than b of I, we'll just swap them up so that all a of I is less than or equal to b of I. So we're just swapping them up. We'll define our dp array as n cross 2, and we'll define our base cases. Then we'll be running a loop from 2 to n. Now we'll just define all of our three cases. So if our a of I is greater than b of I minus 1, then as we discussed, it would be the summation of dp of I minus 1, 0 and I minus 1, 1 plus 1 because we can extend all of the ranges of a of I minus 1 with this a of I. So we can put this a of I to the end of all the ranges x comma a of I minus 1 that we had. And we can also like extend all of the ranges of b of I minus 1. And we are adding 1 because we can start the range at I itself and end the range at I itself again. And dp of I1 would be 0 because we do not want any repetitions. Now, if this is not true, that means a of I is in between a of I minus 1 and b of I minus 1. So if that is the case, we'll set our dp of I0 as dp of I minus 1, 0 plus 1. And if b of I is greater than b of I minus 1, in that case, we can also extend all of those b of I minus 1 ranges with this b of I. Now, the last case, we'll just set this dp of I0 as 1 so that we can start on this index and end it over here itself. And if our b of I is greater than a of I minus 1, in that case, we can extend all of those ranges ending with a of I minus 1 with this b of I. So we'll add the count of all those ranges. And if our b of I is greater than b of I minus 1, then again we'll be adding all the count of ranges which end with b of I minus 1. And in the end, we'll just take the summation of all of them and we'll just print our answer. So yeah, this is pretty much the whole solution in Python. The time complexity is again big O of n. And yeah, that's it for this video. Thanks. Bye-bye.